I'm going to tell you about integrating design time and runtime methods for detecting cyber attacks. But actually, I'm very happy that now I have you as my audience and you can give me feedbacks probably. So I will tell you about the work that we are doing as a group. It's Feridun, our PhD student, Sarah, and other people who helped in this project. So our focus is on cyber-physical system, like Stefano was saying. So we have controllers, we have physical processes, actuators, and sensors. You sense what's happening. There is a controller to control the physical process, and there are actuators to do the actual controlling over the physical processes. So we can call it embedded systems that are controlled and via software, and you also have network here. Okay, and we have these kind of cyber physical systems and transportation, robotics, and production systems. They are all over the place. These are some examples. Now we have vehicle to everything, V2X communication. We have the cars that are actually autonomous. They have to stop when they sense a pedestrian in front of them. We have sensors and some infrastructure that tell us if there is an accident, and we can avoid the accident. We can reroute and all kind of smart things that we can do. But at the same time, now we have these open and connected systems that basically we are widening the attack area. At lunchtime, we were talking about different attacks that can happen when we have such systems. This is another example when we have a robot. This is an ABB robot arm. Here, the parameter that is added is human being. So the robots are collaborating with humans. This lady comes close to the robot, and you can see that it slows down. And if the operator comes closer into the red area, the robot has to completely stop to be safe for this human being to be close to it. So there are many things that are many challenges that we are facing by having these cyber physical systems being open and connected, and also being dynamic and being collaborating with systems, with human beings. This is another example, a water treatment system, and actually a simple password-based authentication is used to control network access. So here we also can have some attacks over this water treatment system. There are PLCs and tanks and pumps and valves to clean the water. And then you can imagine an attacker to want, if the attacker wants to attack this kind of system. So we have this security challenges for cyber physical systems. And I was asking questions, and this is my point, that these attacks can be either on communication or components. So for us as software engineers, it's simple. We don't need much classifications. We see them as attacks on communication or components. And you were right. So communication is actually, you have to be cautious about bad inputs, what Luciana was also talking about. But for us, still, it's communication and components. There can be attack on these two entities in our cyber physical systems and causes incidents. So the challenge for safety security engineers is that they have to define rules, do some kind of risk management, and have to define rules and policies and put them in this intrusion detection systems that help detecting the attack and maybe doing something about it, or just stop the robot. That's the least thing that these IDSs can do. So this is not easy to derive this from the specification documents of the system. And when you have the rules, you also have to move them to design and implementation. So what we want to do is to have this kind of attack detection and prevention in cyber physical systems. We use formal verification. Our background is in formal methods and formal verification. We use it at design time. We also do a monitoring at runtime. And at runtime, we use a tiny digital twin. So the summary of what my message or the summary of what I'm going to tell you is that we have a model, because I was talking to Stefano, we don't use AI at this point. We have a model of the system based on the specification, actually like what Sarah was saying, that's how we build a model from the specification. We are doing some work with a master student with ABB robotics, just reading the specification that they have, safety specification documents, and derive the model, the behavioral model. Using that model, we do formal verification at design time. Then we have a model and we have the state space of the required or the good system, the good behavior, the required behavior that we want. We use it as some kind of digital twin. So we put it there. And by looking at that, we know if the system at runtime is doing what we expect or not. That's what we have done in a nutshell. So the impacts are that we can find anomalies and possible successful attacks, including compose and coordination attacks in a semi-automated way, and also make this attack detection process systematic for safety and security engineers. We can provide concrete traceable reports and extend the approach for recovery and adaptation. We are just, this is our future work actually. So the work that Sarah was talking about with Stefan, for example, he told us that we sit around the table, we talk and we derive all these safety or security attacks or actually risks that can be there. But what we do, we just derive that from the model. What can go wrong in the communication or in the component. So here we have our monitor, and here we have our tiny twin. And this is just sitting on the way of control commands and also sensor data, and listen to input and output of the controller and drops faulty commands if it can identify a mismatch between the transitions in the tiny twin and in input and output. So and from that, we also can provide a report to show sources of the attack. So the idea actually comes from this MAPE-K loop idea from IBM in software engineering and autonomous systems, that they have this system here and they monitor the system. Here, they have this analyzer planner that can detect and adapt, detect the attack or the fault and then adapt to it. Changes in the system or outputs to adapt to this situation. So the idea comes from that. And in this MAPE-K control loop, they also have this K is knowledge, which is a model that they keep at runtime, they call it model at runtime. And here we have it as our tiny digital twin. So we use the idea of MAPE-K and use that in our intrusion detection system. So at design time, what we do, we have our design models and requirements and map them to assertions. This is actually what Bjorn asked Sarah. So this is mapping of requirement to assertions. Also, we have some UML diagrams, probably. That's the work we did with Luciano, having UML diagrams from, again, the specification documents in the company. So we built our Rebeca model out of that, and feeding in Rebeca and as the Rebeca code and the assertions to the model checking tool, we can receive the formal verification results, which is the state space. And also if there is a counterexample, we see what's going on. So Rebeca, I will show you later. It's like a Java code. So It's nothing scary, formal, or scary in that. It's just like a code. And here, after that, you can just debug. This is the iteration for debugging. And then we also map it to Lingua Franca, which is a wrapper over several languages like C++ or ROS that can be, it's executable. So you can run it on your PLC or on your robots. So we actually completed the cycle from design models to an executable code. And as I told you, it's an iterative process. So you have to go back and forth between requirements, behavior model, formal verification, Rebeca model, LF, and you may find bugs and you have to go back and forth like other processes in software engineering. Okay, so at design time, you can identify successful attack scenarios on this water treatment system, for example. You have, as I told you, you have PLCs and tanks and pumps and valves, and quite a few of them. And on this example, and you can find the code on our GitHub, we modeled 105 attack scenarios on communication, which is basically changing the input to something that you're not expecting. So something that attacker can do, changing the input. And 84 attack scenarios on component. Can you guess what that can be? Just not to let you sleep after lunch. So attacks on components. On communication, I think it's clear. It's changing the input from the sensors. What else actually here it can be? Also output to the, yeah. Okay. Yeah, also output to the actuators can also be changed. These are the kind of attacks that we modeled here. Where's my cursor? That was my cursor. And this one is components. You change the code. So attackers can just deliberately change the code, like an if then else or an equal to, less than or equal or something. That's what attackers are doing. So these are the things that, this is how we play with our Rebeca model, which was correct in the beginning, and model these kind of attacks. We also modeled more than 8,000 combined attacks. So all these attacks that I told you, then we combine them, have more than one of them. And then we have 29 cases of successfully violating the system security. So again, this is what Stefano was talking about. So you have all these attacks and only 29 of them can really bring the system down, not bringing it down, but making it behaving in a way that we don't expect. So not all the attacks were really successful. So this is what we did at design time. And yeah, these are these three schemas that we have at design time: communication, component, and combined. And this is how we map that to stride model. This is more what Sarah is now doing to map what's, because we just see components and communication. But to be able to talk to people in security community, we say what these attacks can be, how these attacks can be done. Like it can be an injection attack or man-in-the-middle attack that boils down to changing something on input or output or on the component. So yeah, and this is the model. I removed something now, I can't remember. Okay, so this is the Rebeca code that I told you. The thing that is nice about our model is that you just write, there is a one-to-one mapping between the components you see in your cyber physical systems, like PLC, tank, pump, sensor, and what you model in your Rebeca model. And there was a question at lunchtime. We also model the physical entities. Sometimes we have to, where you need to check the, basically you need to check the overflow and underflow of the tanks. So you don't care what Stefano was saying, sorry, I quote him all the time, but this is to connect all these talks today together. So he was saying, who cares what you do in the software? Exactly. So if you look at the assertions, we don't care. The assertions are all about the tanks. Do we have underflow or overflow? So we have to also model the physical entities that are important. So for any model checker, you have two inputs, the behavior and the properties. So this is how you write the Rebeca model, which is the behavior. And this is the assertion. So you have to, based on the variables that you have in each of your components, you basically write your assertion, what you don't want to happen or what you want to happen actually. And then you check that. And this is just to show you how you write a kind of Rebeca model. So you have the initial status, you write the if then else's based on what you want to happen. So the code can be, Feridun was telling me it's a one-to-one mapping almost to the C++ code in Lingua Franca. So this is our tool. We have our tool at the Eclipse, in Eclipse environment. You put in the Rebeca model here, you just press model check here, run, and you get back, if there is a counterexample, if something is wrong, you just get back the counterexample here. It shows you the trace, how you are moving to get to this point where the assertion is failed. So, and you see the details of each state here. What are the values of the variables? So I didn't take the risk to run it right now because, you know, on Max's computer and then I blow up everything. So, but trust me, you can run it, press this and you get the model. And if it is satisfied, if the assertions are satisfied, you just see that over there. We have our homepage and all the tools, examples, and publications are there. So these are some of the examples of our attacks at design time. So for example, I'm in state S0 and the sensor to PLC1, I inject something wrong in it. This water level in tank 1 is high. This is wrong. This is actually not true. And then the property on underflow will happen. So you will have this underflow happening. You see that using the assertion. The model checker will come back and tell you. So these are the successful attacks. This is when you change something on the component and you see that things are going wrong. And these are some of examples of the combined attacks when you have changed something also in the messages and in the components. Okay, what we do at runtime, we use the state space that we got from model checking of this Rebeca model. And we also know about the observable actions in this system. And we put that in our monitor. So now the monitor has the required behavior of the system. And we call it tiny twin, tiny digital twin, because we don't put the whole state space, we reduced it based on these observable actions. And although we reduce the size, we still preserve the branching by simulation equivalence. This is the theory behind our work. So this is another example, temperature control system. There is a window, you have, there is a room, it has a window, so the temperature can change. And you have a heater and cooler unit here. You send a controller, sends the commands to that, and you have your sensor here. So the commands are activating heater or the cooler or switching it off. And the sensor data is, of course, the temperature values. This wireless communication network is vulnerable to malicious cyber attacks. And these are the types of attacks that can happen: eavesdropping, dropping packets, false sensor data injection, or faulty control commands. And this can degrade the temperature regulation process. And then you can push temperature value out of your desired range. So the abstraction is like this. You got this big state space with 76 states and 103 transitions, and then you reduce it to 21 and 36. How? you just keep these actions: time, get sense, activate, and switch off. And then the others, the internal actions like heating and cooling, are hidden. Then you merge. This merging can be tricky. It can go, actually can go wrong easily. We use a well-established tool for that, but we had to map our output to their input. And that was, again, we used the theory there. So, so this will be our tiny tool. So we have the required behavior of the system inside the brain of our monitor. It's sitting there, so you can check. You walk over this state transition, this state space, together with the system, and make sure that it's walking on the desired path. So this is an example. You're sitting here, the temperature is 23, and in your system, you know that you cannot jump more than 1. So if there is an injection of false sensor data temperature 21, you see that this cannot happen. This is not a valid output of this state. So you can, you notice that there is an attack. Another thing is that you're here, the temperature is 24, and then there is an activation of the heater, and you say, you see that, okay, this cannot happen. So you just detect the attack here. And it's like in a robot, if you see the human operator is close to you, but the standstill function is not enabled, there is something wrong. So you are in a state, the operator, the sensors told you that an operator is close to you, but standstill is not enabled. So there's something wrong. But there are attacks, like stealthy attacks, that actually Alessandro was asking about, that we cannot detect. Like you are in 23, you are in temperature 23, and you get 23, but this is not true. So actually it's cold, but the sensor is telling you that it's 23. Then you need other rules. You need some meta rules. You need to know it's not likely that you stay in 23 degrees in October in Sweden. So those meta rules shall come and be added to your transition system such that you can also detect this kind of stealthy attacks. So everything is fine on the transition system, but you know that this is really not good. So you have to add this kind of metadata to your branches. This is the ongoing work of Feridun. Hopefully for in a few months, we will be done with that too. So, okay, for this system, we again had all these attacks being modeled, and we found this is now at runtime, so we can just have an alarm going off if something goes wrong. The detection rate is around 68.8. And that's all the case studies and examples I wanted to tell you. And for a car, this may not happen because the state transition, this may not be useful because writing down the model of a car, autonomous car, and what are the required states and transitions, it's not easy. But if you can have some kind of abstraction, like, I don't know, I better not try to make an example here, but it's for a robot, it works. For production systems, for factories, it can work. In a car, I'm not sure. So why we're using Rebeca? Because it's friendly. What do I mean it's friendly? It's not too much mathematics behind this. It's not algebra. It's just for software engineers, it's friendly. They like to use it. They can learn it quickly. I have experience with that and with engineers. And it's friendly to cyber physical systems because the model is actor-based. So it's all the actors, it's concurrent objects. So we have all these actors. You can model components using these actors. Actors are sending messages to each other. So it's just like a network, and you don't need to model the queue. So if you use process algebra or timed automata or those kind of models, you need to model the queue, and I just removed all the slides about that, but they will explode much faster than our model. And it's much easier to model these kind of network-based asynchronous systems using Rebeca. And these are just some examples. This is for a medical device that it's using publish subscribe and actually other patterns of communication. But this is just one example that I brought here for you, that you just get all these components there. And if you have this kind of sequence of message passing between them, so any kind of network protocol, you just can model it using Rebeca. You see that here. And this is another kind of network example. You have network on chip, some kind of architecture, all-spin architecture, and all the routers, you can just, again, model it. You have the router, you have the core, you have all the neighbors that you send messages to them. You can just easily map what you see in the real world to your model in Rebeca. And why Lingua Franca? We mapped Rebeca to Lingua Franca because we wanted to close the loop. You can run Lingua Franca, and it is also actor-based. It's wrapping all these target languages. We use the C++ code, which is closer to what we want to run on a PLC, for example. And it takes care of timing. I won't dive into this. This is another talk for itself, because we care about time systems and we have logical time. Lingua Franca actually keep these physical time and logical time in sync. And there is a very natural mapping between Rebeca and Lingua Franca. So it's easy to map Rebeca to Lingua Franca and run it then. So future work, adaptation techniques, update the tiny digital twin at runtime with respect to system changes. I still don't know how we are going to do that. Mitigation plans, recover the system after attacks. I don't know if this is doable. Using machine learning mechanisms to improve the detection rate of the monitor module, extend the scalability of the monitor in large distributed systems, and backtracking, showing most critical attack points in the system. This is working on causality, for example, which is a very interesting subject. So I'm done. Thank you very much for listening. Any questions? I'm chairing myself. I need an order. It's leaning.
Basically, the first question would be, where would you see the system? Like, where would you place it?
What do you mean?
You said you will put it between controllers and then actuators and sensors.
Yeah.
Do you think that's or is it like an independent system, like all on its own, or is it located in the PLC itself, or
so
where do you place the system?
For example, for these ABB robotics, they have this safety computer. So they have it there for safety. We can put it there somewhere, this monitor, or in the controller, if they allow us.
That's basically the second question, is how do you deal with time critical applications?
Time critical.
Because basically you reading the input and resending it out, if that's the case, what's happening, like based on the picture, it looks like it, or if you're just passively sniffing it, I don't know. Like, how do you deal with those?
So in all these safety critical, not all, in the safety critical systems that I've seen, for having fault tolerance, they have this kind of redundancy. They are sniffing, what they don't call it sniffing, I think, but they have this extra computer that knows all about it. So they already have this kind of machine. So in a car, we were talking, in a car, I cannot imagine how to do that. But for a robot, they already have that. And it's from our experiments,
on water, for example, PTA, that supporting those security patch we can take care of the money for if we are caring about the time, we know that this time is in our code development monitor that's running on this.
Thanks.
So maybe this is an obvious question. If I understood correctly, this is only about safety implications of cybersecurity attacks, right? It's not general IDS system.
Yeah. What does that mean? But okay.
Well, you know, in cybersecurity in general, we would say that if the attacker can read one bit it shouldn't read, then you have failed as a cybersecurity engineer. So, but here you only care about
yes.
the physical.
Yeah. If it impacts the, yeah, exactly. That's why I was referring to Stefano all the time.
Yeah, I'm a little bit unsure, but you have digital twin that executes the same code or that monitors.
Just monitors. So,
Just monitors.
yeah, so the monitors look at this digital twin. It's like a model of the system, the behavior of the system, the way it should be.
Yes.
Yeah.
And you have an intrusion detection to evaluate whether your system behaves as it should.
Yes.
What is your reaction if the intrusion detection identifies a deviation? Will you stop the system, or what will happen if the IDS gives an alert?
We can stop the system.
Sorry?
We can stop the system.
Can stop.
So that, yeah.
So is your model or your digital twin an oracle here, in that sense that it knows exactly how the system should work?
Yes.
And I'm a little bit curious now. This is an open question. How much security mechanisms do you need then if you know exactly how it should behave?
How much?
How much, or which security mechanism, how much mechanism from security point of view do you need if you know exactly how it should behave? Because if it misbehaves, you know that. And
Yeah, that's what, yeah, for these cyber physical systems, for example, you know that the tank shouldn't underflow or overflow. So you know it. So, and then when you're sending a command to close or open a valve, but your digital twin shows you that it shouldn't happen, then you can stop it. So then you notice it and you stop it. Or in all these systems that you know, for example, if this piston is down, the other one should be up. Then if something is going wrong, or if the robot, if you see that this robot is in this situation and that someone is coming in, but so then these are the situations that you can do something about, and you just can't stop. And I can first let's finish this. So what is your question then?
It was more, if you know that your digital twin monitors and that one can decide if you have a deviation.
Yes.
Then I'm thinking about situations. What are the situations then where you also need cybersecurity there?
Like
which
what?
Mechanisms, for example, to make sure that the signals are correct, or that you get the right commands, or how much can you limit the cybersecurity mechanism needs, since you have the model that runs that says what is the correct
for
behavior.
example, you can shut down the firewall if we have this timing. That's what you're saying.
If somebody tries to send a command that should not be sent, then your monitor should identify that and then stop that command.
Yeah.
So I was curious how much cybersecurity to that level is needed if you know that these commands are only coming at different times, or because you know the behavior of the system.
I understand what you say. I didn't think about it like that, but we just say that we have all these levels for cybersecurity. So we assume that we have those, but the attacker already passed that. And now we are in this situation. That's our assumption. You wanted to say? You're saying that's useless. Just throw them out. The other cybersecurity things are useless.
The question is to what extent are they needed if we monitor one oracle, what part of the system should be taken? Because if there is a deviation, we should stop. So yeah, it's a question. This is a question kind of how much cybersecurity mechanisms are needed now.
Yeah, for example, that 23 degree, if the attacker just keep you in 23, the oracle cannot realize that. Those kind of stealthy attacks, unless you have these extra data, metadata over them. And Feridun wanted to say something.
Yeah, to complete your answer, it depends the source of the text. We find which sources is compromised, and based on those sources, we use a security mechanism, for example, for blocking packets or dropping the malicious packets. So it depends on the reports it's provided by monitor. So the expert in the security knows what to do after that. So identification and correct localization on this component or communication is very important.
There are two other questions. If you're done with the question.
Yes.
And while you, okay, and the project that we have is about not to stop the robot.
Okay.
So that's what they asked for. But up to now, I think, I don't know what to do. You tell me what to do, I do that. How can I decide what to do with this robot? I will just stop it. The most thing that we can do is not to stop all the robots, just stop the robots that are in the area of risk. We couldn't think of anything more yet.
Added to the whole system, whatever system.
Yeah, I guess you can say that. This is some kind of IDS, fancy IDS.
Okay. And then I was thinking if it's some component that is added to the system, then in this component you are thinking, okay, how I control the system so you wouldn't get any attack. But I was thinking, how about the attack would be to that component, to the cybersecurity component?
Yeah, we secure that in the old traditional way, like when everything was safe, with no wireless connection and just in a safe area. Yeah, that's what these people, you're doing this. That's what I learned from your community. I was asking the same question, but they afraid until yeah.
Sorry for complicating this. There is some hardware that this hardware provides to you some secure module that you can use it to monitor on that hardware. But usually PLC is using some hardware that you just run a simple code, not complicated or encrypted module or something like that. So we run the monitor, and the one hardware have enough power. So it's easy to secure the monitor in one layer and take control of the system in different layers.
Shall I answer your question or shall we move on?
I have a question. The slide where you have the water levels, you were shooting the bounds that if the water level does not go up or down, that it can compare with the injected range. So my question is that the whole logic is on if it is something out of these bounds. What if the water level is increased from 9 to 14, then the limit was 15, but now still it is higher under the cyber effect. So if this is the situation where we have not crossed the safety or that limit, but still we are under attack. But in this situation, it will not be. The same happened for the Stuxnet. And around the nuclear program, the centrifugal speed, they just increased it. It was not like that. They
You're right.
crossed the limits. So maybe safety is breached. So maybe safety is not breached, but still it is not secure. So if the detection is based on these bounds, then how do we define that we don't cross the bounds? Then the detection would not.
Yes, that's the kind of attack I told you. We still don't have any. Can you put it on the next person, please? Like this 23 is exactly like the question you asked. It's within the range, so it can be 20. Then you need some kind of meta rules. I don't know what they did. I don't want to talk about that attack, but but for example, you keep the tank. Then you need other data to find out. That's like this 23 degrees that I told you. You need other data, like that's where AI comes in picture. So in this kind of weather in October in Sweden, it's not natural to stay on 23, or the tank shouldn't be on 14 for more than 10 minutes. You need extra rules for that.
Extra requirements maybe.
Yes, yes, yes. I think that's what they call stealthy attacks. So we need extra information. Thank you very much. Sorry for going over time.